All right, let's just jump right in, shall we? Welcome to this explainer, where we're going to unlock one of the most exciting, fundamentally crucial engineering puzzles in the entire world of digital logic. I'm talking about binary subtraction. If you've ever found yourself wondering how the microscopic silicon inside your computer actually does complex math, well, you are in exactly the right place. We're going to break down the mechanics of the full subtractor piece by piece. So let's get into it. It's a pretty fascinating question, isn't it? You might naturally think about how you personally subtract numbers, right? Borrowing a 10, carrying things over on a piece of scratch paper. But how do computers manage multi-bit arithmetic? The truth is, simple logic gates on their own actually fall really short when things get complicated. They need a highly specific structural hero to handle the heavy lifting for them. To figure out how they do it, here is our roadmap for today. First, we'll tackle the binary borrowing problem. Then we'll look at the anatomy of full subtractors, decoding the truth table, simplifying with K-maps, and finally, building the logic circuit. All right, part 1, the binary borrowing problem, which is really the core issue here. So the crucial point we have to understand first is the difference between these two circuits. In digital logic, we have something called a half subtractor. But here's the catch with that one. A half subtractor can only subtract the least significant bit, the LSB, of binary numbers. It effectively drops the ball when sequential borrowing is needed, because it completely ignores any borrow generated from a previous stage. It just doesn't see it. And that introduces the absolute necessity of the full subtractor. The full subtractor is what saves the day. It handles multi-bit subtraction because it actually considers and accepts the borrow from that previous stage, ensuring our math is actually accurate. Moving right along to section 2, let's look at the anatomy of full subtractors and their digital logic structure. Okay, let's get our basic terms straight before we get too deep into the weeds. We basically have 3 key players. First up is the minuend, which we represent as A. This is simply the number to be subtracted from. Second is the subtrahend, or B. That's the number we're subtracting. And finally, the real star of the show, bin, or borrow-in. This is that crucial borrow passed along from the previous subtraction stage. So if you picture that combinational circuit in your head, we have exactly 3 inputs feeding into it, A, B, and bin. Processing those inputs gives us 2 essential outputs on the other side. The first output is the difference, which is exactly what it sounds like, the actual result of the subtraction. The second output is borrow out. This tells the rest of the circuit if a borrow is going to be needed for the next stage of calculation. It creates this perfect, unbroken chain of information. Which brings us to section 3, decoding the truth table and all its logic combinations. Now, I know truth tables can sometimes look a bit dense, but this is literally the raw visual anchor for everything we're doing. It maps out all 8 possible combinations of our inputs, A, B, and bin. Just look closely at when the difference, or D, turns into a 1 and when B out becomes a 1. Like, obviously when all inputs are 0, everything is just 0. But check out that second row. When A is 0 and B is 0, but bin is 1, our difference suddenly becomes 1, and we generate a borrow out of 1. The exact same thing happens if A is 0, B is 1, and bin is 0. And if you skip down to the very last row, where A, B, and bin are all 1s, both our difference and borrow out are 1. This table right here is the foundational logic map of subtraction. Next up, section 4. We are simplifying with K-maps to derive our logic expressions. Okay, to translate that truth table into something we can actually build, we use Karnaugh maps, or K-maps. Look at step 1. We start with this rather intimidating basic expression for the difference output. We're literally just grabbing every instance where the truth table output was a 1. But watch how we simplify this down into a really digestible procedure. In step 2, we just factor the common terms. We pull out bin and bin not. Then, for step 3, we substitute using our XOR and XNOR properties. Because A naught B naught plus AB is just A XOR B, and AB naught plus A naught B is A XOR B. And look at how beautifully that cleans up. By substituting those XOR properties, we arrive at this elegantly simple final equation for the difference. D equals A XOR B, all XORed with bin. What started as this massive, clunky string of variables just collapses down into a highly efficient logic gate structure. Now, we literally just rinse and repeat that exact same step-by-step process to build our borrow out expression. Step 1 is our basic expression for borrow out derived straight from the truth table. In step 2, we factor those common terms, pulling out bin and A, not B. And for step 3, we use our XOR and XNOR properties again, specifically using the XNOR identity, to condense those factored terms down. And ta-da! Revealing our final equation for the borrow out, B out equals bin ANDed with the not of A XOR B plus A not B. The K-map perfectly handled all the complex logic required to carry the borrow to the next stage and wrapped it up in this incredibly optimized mathematical bow. All right, final stretch. Section 5, building the logic circuit and its physical design. So despite all the complex math, the truth tables, and the K-map factoring we just went through, you know what the magic number actually is? It's 2. Just 2. Physically implementing a full subtractor actually only requires 2 half subtractors. Here is the final, elegant recipe to physically build the circuit in digital logic. You take 2 half subtractors, combine them with 1 OR gate to handle the borrow out logic, and boom, you have exactly 1 full subtractor. It is an unbelievably efficient use of logic gates to solve a really tricky multi-bit problem. So why does all this actually matter? Well, I want to connect our journey today directly back to the real world. As our source notes, because the full subtractor handles borrows, it is directly suitable for multi-bit subtraction in arithmetic logic units, or ALUs. The ALU is basically the mathematical brain inside the CPU of any computer, phone, or smart device you own. Without this exact logic circuit, modern computing literally couldn't do the math it needs to function. It would just be a very expensive paperweight. So I want to leave you with this provocative thought as we wrap up today. Take a second and look at the device you are watching this explainer on right now. Inside that exact machine, how many billions of these tiny, perfectly structured logic circuits are working together, passing borrows and calculating differences at the speed of light? Just to stream this video to your screen? It is a staggering scale of engineering, and it's all built on the elegant foundation of the full subtractor. Thank you so much for joining me on this deep dive today. Keep asking questions and keep exploring the incredible logic built into the world around us.